Hello friends, welcome to the thermodynamic aspect of polymeric system. Now thermodynamics play a very vital role because sometimes the heat of reaction, sometimes other exothermicity or endothermicity plays a very vital role in the polymeric system or polymeric reaction mass. So the knowledge of all these things, and you can say this is the backbone of your polymerization process and a polymer system. So the awareness about the thermodynamic character of the polymeric system is extremely important. So by this way, we are starting this thermodynamic aspect of polymeric system under the edges of polymer process engineering. So let us take up with the first segment of this thermodynamics aspect. Now in this particular segment, we are going to cover what is the thermodynamics, then we will discuss about the polymeric PVT data, then we will discuss about the equations pertaining to the equation of state, especially with respect to the polymer system. Then we will discuss about the polymer calorimetric data. Now, the thermodynamics usually is the study of the relationship between the heat, energy and work, or among the heat, energy and work, and how they affect the various properties of any system, chemical species or polymeric system. In principle, the thermodynamics which can be applied to the wide range of the materials system, this including the polymer. Now, since the polymers are the large molecules made up of a repeating units, they are called the monomer. So, they are used in a wide range of application right from day-to-day affair to the specialized thing. Now, the thermodynamics of polymeric system is usually concerned with the understanding behavior of the polymer in different conditions pertaining to the pressure, temperature, chemical exposure, atmospheric exposure, environmental attack, all these things. So, the thermodynamic property, the knowledge of the thermodynamic property is quite essential. The thermodynamic properties of polymers, they are influenced by the molecular structure of the polymer and the degree of polymerization and the chemical composition of the monomer. Now, these properties can be studied by using various techniques like instrumental techniques like differential scanning, calorimetry or thermal gravimetric analysis. Now, usually these techniques measures the thermal behavior of the polymers or weight loss of the polymers, and usually they are represented as a function of temperature. The thermodynamic of the polymeric system, this also plays a critical role in understanding the behavior of the polymers in various industrial and engineering application. Let us take an example. The thermodynamic principle can be used to predict the stability and the shelf life of polymer in different environment. Like if you are using any chair from 0 degrees Celsius to say 47 degrees Celsius atmospheric temperature, then how you can predict the shelf life of a polymer up to how long it go to in a workable situation. This can be the thermodynamic data is useful in predicting such kind of life cycle analysis. Now, to design the polymer with specific properties, because sometimes you are having the granules and you need to convert all these granules into the useful product like chair or any commodity item, then you require the heat and energy. In that particular aspect, the knowledge about the thermodynamic principle is quite essential. And to optimize the processing condition of the polymer production, the thermodynamic data gives a useful information. Just for example, suppose any polymer melts at say 60 degrees Celsius. So, you cannot go beyond 100 degrees Celsius, otherwise it may tend to have a different properties. It may get charged. So, all kind of thermodynamic data is quite essential. The knowledge of all these data is quite essential. So, the overall study of the thermodynamic of polymer system is important for understanding usually the fundamental properties and the behavior of the polymers, as well as the developing the new material and application that can benefit from unique properties of polymer. Now, usually thermodynamics is governed by the various laws, and in practice there are 4 laws: zeroth law, first law, second law, third law. So, these laws, they supplement to various thermodynamic principle, and based on these principle and laws are various kind of thermodynamic equations being derived. One of the important law is the first law. So, the first law of thermodynamics, which is known as the law of conservation of energy, states that energy cannot be created or destroyed, only transferred or converted from one form to another form. For a polymeric system, this means the total amount of energy within the system remains constant but can be redistributed among its various components. Now, this includes the internal energy of the polymer chain as well as any external work or heat is then added or removed from the system. So, the first law of thermodynamics, this can be expressed mathematically, that is delta U is equal to Q minus W. Delta U is the change in the internal energy of the system. So, if you supply any, or it can be modified like this, Q is equal to delta U plus W. So, if you supply the Q amount of heat to the system, then certain quantity of the heat can be consumed to raise or to alter the internal energy of the system, and remaining you can utilize as a work. So, W is the work done into the system and delta U is the change in the internal energy of the system. So, this equation can be used to calculate the change in energy within a polymeric system due to the external factors like change in the temperature, pressure or mechanical stress. So, in a differential form, this thermodynamic law can be represented as du is equal to dq minus dw. Du is the differential change in the internal energy, dq is the differential heat added to the system, and dw is the differential work done by the system. So, sometimes in thermodynamic system, this the dq is represented as dq is equal to mcd delta t. So, dw or work, this can be represented as dw is equal to fdh, where f is the force being applied or acting to the system and dh is the differential change in the distance or height, whatever you can say. So, if we substitute this particular these things into the differential form of the first law of thermodynamics, which we represented over here, we can get the modified equation of du is equal to mcd delta t minus fdh. This equation describes the differential change in the internal energy of an elevated system due to the differential change in temperature and height. Another thing is very important, that is enthalpy, because when we heat the system, then we must know about the thermal behavior or response toward the thermal behavior of any polymeric system. So, the enthalpy is a useful tool to get this kind of information. So, this can be defined for a system involving the expansion of work PV, because sometimes polymer is composed of the chains. So, if you heat, then definitely the chains are unentangled to give the some sort of expansion work. So, this can be defined, this can be very good predicted by the enthalpy. So, the enthalpy mathematically can be represented as H is equal to U plus PV. This is the very generic equation. V is the specific volume, U is the internal energy and P is the pressure. Now, Cp, sometimes the change in the specific heat at constant temperature is again very useful, which has the unit of joule per kilogram Kelvin. Now, Cp is equal to dH over dt at constant pressure. This is again a very useful tool. So, therefore, the enthalpy for constant pressure system can be represented as dH is equal to Cp dt. The specific heat associated with the constant volume is defined as Cv is equal to delta U over delta T at constant volume, and then Cp minus Cv is again very useful thing. This can be given as T epsilon square over rho beta. Now, epsilon is the coefficient of thermal expansion. Now, it is quite evident that whenever you are heating any polymer, then there may be certain expansion attributed to the chains and all those things. So, you need to have this particular information handy. Now, the coefficient of thermal expansion can be given as epsilon is equal to minus 1 upon rho del over rho del rho over del T at constant P. This can be given as 1 over V into del V over del T at constant P. Now, in the previous equation, we use this beta. This is the compressibility factor. So, compressibility beta can be defined as beta is equal to 1 over rho over del P at constant T, and which is equal to 1 over del V over del P at constant T. So, the change in the enthalpy at constant temperature with pressure is given as dH is equal to V minus T del V over del T at constant P into dP. For a steady flow system, it can be represented as delta H is delta H plus change in the potential energy plus change in kinetic energy, that is equal to Q minus Ws, where Ws is the shaft work and these are the potential energy and kinetic energy, and Q is the heat flow in the system. Now, the second law of thermodynamics. Again, it is impossible to convert a given quantity of heat completely into work. So, the property associated with the second law is mainly the entropy, which is usually represented as S. So, for non-flow system, it can be ds, which is greater than equal to dq over T, where T is the absolute temperature. Now, similarly, if we talk about the flow type of a system, then ds is greater than equal to summation dq over T plus Si in and out. So, the other properties, when we talk about the other properties in the thermodynamics, this includes the Gibbs free energy and Helmholtz free energy or Helmholtz work function, which can be defined as the Gibbs free energy. This is represented as G, H is enthalpy, T is temperature, and S is the entropy, and Helmholtz work function or Helmholtz free energy. This can be given as A is equal to U minus Ts. U is the internal energy. So, the entropy change at constant pressure, this can be given as ds over dt at constant pressure, that is given as Cp over T. This is a general thermodynamic equation. And the change in the entropy at constant pressure, this can be defined as ds is equal to Cp over T dt. Now, similarly, the entropy change at constant temperature with changing pressure, this can be written as del S over del P at constant temperature, that is minus del V over del T at constant pressure. This is sometimes referred as the Maxwellian equations. Therefore, the change in entropy in the differential form, which we can represent as ds is equal to minus del V over del T at constant P dP. So, let us talk about the polymer pressure, volume, temperature data. Now, see, the pressure, volume, temperature, the PVT data, they are very important. The reason is that if we need to define any kind of thermodynamic system, or especially any kind of a system with respect to the thermodynamics, there are 8 different parameters needed, and out of 8, this can be the pressure, volume, temperature are only 3 parameters which you can measure directly. So, therefore, the pressure, volume, temperature, these data are quite important, and these data are quite important to measure, because for rest of the data like enthalpy, entropy, other things, you need to have a correlation which can be developed through this pressure, volume and temperature data. Now, this calorimetric data, again, the CP data or CV data, these are again very important. And these two, PBT data and the calorimetric data, are the two fundamental pieces of information which need to calculate the thermodynamic parameters like enthalpy, entropy, all those things. Now, it is also feasible to employ the suitable calorimetric equations and equation of state. This is relating to CP or temperature for all these goals. Now, the volumetric behavior of polymers, now sometimes the temperature and the pressure is an important aspect of many polymer processing equations. So, therefore, such behavior is important for any kind of a polymer engineer or scientist. Now, here we have depicted some plots for actual PVT data of various polymeric systems. Now, depending upon the values of temperature and pressure, we can calculate the specific volume of the material. This particular figure is showing the increase in the temperature, the specific volume of a polyethylene. Marginally, this changes with the increase in pressure. And the usefulness of this particular data is that beforehand, if you go for any kind of a polymeric process, or you are going for like extrusion, or if you are going for any kind of a molding, all these things, this kind of a behavior, because there will be a continuous rise in the temperature. So, this particular behavior, how much volume change and how much, because of the volume change, some sort of the pressure change may occur. So, all these kind of information is extremely important in this aspect. Now, if we see that before 125 degrees Celsius, that is a limiting temperature, the specific volume with increase is in pressure is minimum. After say 125 degrees Celsius, the specific volume gradually starts decreasing with increase in pressure. So, at constant pressure, the specific volume is directly proportional to the melt temperature, and this is why, the determining how effectively control of injection speed in the injection molding machine and the switchover position in order to stabilize the pressure curve is very important. And the knowledge about all these curve beforehand is extremely crucial and useful. The solid polymers, these can be broadly classified in two general areas which discussed in some of the lecture, like amorphous and semi-crystalline. The semi-crystalline polymers, they exhibit a melting point and form melts. The amorphous polymer do not melt but only thermally soften. So, the better insight, see again we are going to discuss the temperature behavior of these polymers, semi-crystalline and amorphous polymers. So, before better insight, this can be obtained, and this is given in this particular figure, where the specific heat behavior for any particular polymer, for an amorphous or crystalline polymer is given. Now, as you can see here, the semi-crystalline material shows a definite peak at its melting point, whereas the amorphous polymer material gradually increases. Now, similarly, the semi-crystalline material, this will undergo a significant volume change at constant temperature for a given pressure. So, such an occurrence is the first order transition point. Now, this particular figure refers the volume change at constant temperature for nylon. Another, if we take the polyisobutylene, this is the effect of specific volume versus temperature. So, the amorphous polymer, on the other hand, will not have the melting point and attendant volume change. So, you can see the behavior of these curves. So, all polymers, they do undergo second order transition, which occurs when the volume temperature curve at a given pressure undergoes a discontinuity, but not a volume change at constant temperature. So, the most important of these transitions in the glass transition temperature, because ultimately it reflects the molecular weight distribution and several properties are attributed to this glass transition temperature. Now, this particular figure shows the occurrence of such point of atactic polypropylene. Now, here you see this is the glass transition temperature. So, the glass transition temperature, again in a modified form, that they represent the point at which polymer segments here this go only the vibrational motion, that is the frozen in the glassy state, to at a first short range and a later long range diffusional motion. This change is usually marked by a significant reduction in the modulus of elasticity of the polymer. Now here you see that the second order transition, this can and do occur in polymers, which is represented in this particular figure. Here the pressure, volume, temperature data, this shows the discontinuities for the solid polymer, and that cannot be attributed to the glass transition temperature. So the behavior represents their unknown second order transition. Now incidentally, the shift of this discontinuity with pressure is about say 0.016 degrees Celsius per atom. Here you see, which is compared to a general range of such shift, say 0.013 to 0.018 degrees Celsius. Now let us talk about the equation of state. Now equation of state, they play a very vital role, and all of us are aware about the equation of state pertaining to the gaseous systems, like PV is equal to nRT. This PV is equal to nRT is again the equation of state. So once you have a pressure volume data, pressure volume temperature data, this is the equation of state can be generated, and it gives the perfect, you can say, the knowledge about the particular state the polymer possesses. So the real experimental pressure volume data, they are the most effective way to provide this particular information. Sometimes you need to refer the, suppose a particular system moves from this state to this state. In that case, you need to have a equation that reflects that how gradually the system changes. And for this particular purpose, the pressure, volume, temperature data, sometimes empirical data and sometimes experimental data. So if you have some real experimental data, they are very useful to predict the state of that particular polymer mass at appropriate time and temperature and pressure. So this information is sometimes is not accessible and also difficult to ascertain. Now as a result, the necessary equation of a state must be created, because every time you may not have a ready-made equation. So therefore some of the equation must be created. Now these equations enable accurate interpolation of already present data. Now the equation of a state should meet certain criteria in case of polymer. Now these criteria, these includes the equation must be applicable over wide range of temperature and pressure. If possible, the equation should be generalized. The equation should apply to a large number of different polymers rather than one particular polymer. Now the equation should be such that it can be used to predict the behavior of polymers for which no pressure, volume, temperature data available. Ideally, we should be able to calculate pressure, volume, temperature data for a polymer where only easily measured physical properties are known, like glass transition temperature or glass temperature at atmospheric pressure, melting temperature at atmospheric pressure, density at room temperature and atmospheric pressure. So all equation of state have their merits. It is recommended that the two equation based on corresponding state theory be used. The reason is that these represent the generalized equation that depend only on a set of common parameter and on easily accessible data, like polymer density at room temperature and atmospheric pressure, glass transition temperature at atmospheric pressure. Now there are, because we are discussing two classes of polymer, like amorphous polymer and solid semi-crystalline polymer. So sometimes some of equation may be very useful for predicting these data. So for amorphous and semi-crystalline polymers, this equation can be represented as V is equal to 0.01205 rho naught to the power 0.9421 and P to the power n minus 1 T over Tg m plus 1 R. Now, the volume, this is represented in centimeter cube, and the pressure is represented in atmosphere. The temperature is represented in Kelvin, and the glass transition temperature, at atmospheric pressure. R is usually our gas constant, and which is having the units of cubic centimeter atmosphere over mole per Kelvin, and rho naught is the density which is represented in gram per centimeter cube, and N and M are the terms, they are the functions of pressure. Now, similarly, for molten semi-crystalline polymers, the relation can be represented as V is equal to K T over Tg to the power x P to the power y. Here x and y, they are the function of pressure, while K is the function of rho naught with units of centimeter per over gram per atom. Now, the volume change due to the melting of semi-crystalline polymers can be calculated as delta Vm, because the volume change, whenever you heat the segment, then obviously there may be a change in the volume, or if you cool down the polymeric mass, then there may be certain contraction. So, it's quite evident that you need to calculate the volume change. So, delta Vm is equal to 0.19 Tm over 298 Vw, where delta Vm is equal to change in molar volume on melting. Tm is the melting temperature, which is represented as Kelvin, and Vw is van der Waals volume centimeter cube per mole. Now, data from the polymer calorimetry, they are crucial for determining the thermodynamic properties as well as eventually for the design objectives. So, once you design any kind of a polymeric system, then it is quite essential to have this kind of a data. Now, it is equally critical to offer suitable correlations when the experimental points, they are scarce and non-existent in order to estimate such data. Now, let us talk about the correlation for polymer calorimetric and latent heat data. Whenever possible, actual experimental calorimetric data should be used. Frequently, however, this cannot be done. Every time you cannot go for this kind of a calorimetric data. In such situation, it becomes necessary to estimate the polymeric data with the help of some appropriate correlation. So, the generation of these correlation is extremely important. So, some of the scientists, they have proposed the empirical relation for the specific heat behavior for both crystalline and amorphous polymer. So, these relations for both liquid and solid, this can be written as C PS T over 298 Kelvin. This is the standard notation, 0.106 plus 0.003 T. Here S is for solid, S is solid. Now, if we take the liquid segment into the consideration, then CPLT over CPL 298, which is 0.64 plus 0.0012 T. This is for the liquid. Now, here the Cp for solid 298 Kelvin and Cp for liquid, they are the Cp values which is calculated at 298 Kelvin, and for calculated from the group contribution of the various organic group of the polymer, and T is obviously in Kelvin. So, the specific heat values of amorphous polymer is given as Cp crystalline is equal to Cp for solid plus Cp for liquid 1 minus x, where x is the degree of crystallinity. Now, additional correlations, they have been developed over the period of time for amorphous and molten polymers. And other scientists, they show that the Cp data for methacrylate polymers could be correlated using the form of Coates equation originally developed for the organic liquid. Now, the similar scientists, they gave a rough approximation of a latent heat of a fusion. Now, here this can be represented as delta Hm over Cp for liquid 298 Kelvin is equal to 0.55 Tm minus Tg, where delta Hm is the latent heat of fusion joule per kilogram, Cp for liquid at 298 Kelvin, then T joule per kilogram Kelvin, Tm is equal to melting temperature, which is represented in Kelvin, and Tg is the glass transition temperature in Kelvin. So, dear friends, in this particular segment, we started the thermodynamic behavioral study of polymeric system. And in this particular aspect, we discussed the PVT behavior, we discussed couple of thermodynamic law and how these law are applicable. Apart from this, we discuss about some of the more thermodynamic character with the different graphs, that how these thermodynamic property play a vital role in deciding the various properties of the polymer, especially for the end properties, and how important these thermodynamic properties for determination of end properties and the life cycle assessment of all these polymers. For your convenience, we have enlisted different reference which you can use if you need. Thank you very much.